Hello everybody, and thanks for watching the video, and welcome to this video today. In today's video we shall be looking at the correction of the Cameroon General Certificate of Education Advanced Level Chemistry 2023 paper 2 section B, inorganic chemistry. So guys, keep in mind that we uploaded that for physical chemistry earlier, so if you haven't watched that, I will recommend you to go and watch that. I'll put a link in the description for your convenience. Thank you very much. And we shall explain with good examination hints that can help you to attempt and solve all the problems you meet on in chemistry. So guys, as soon as this video ends, we are going to upload that for organic chemistry, and you can only have access to that, guys, if you subscribe to the channel. So please hit the subscribe button and like the video, because that does motivate us to keep producing more and more content. The more like we see, guys, the frequency at which we are producing more content. Thank you very much. So guys, let's dive straight into it. Alright guys, the first question is saying that iron and manganese are transition metals. Roman 1, we should define a transition metal. Then, using the boxes below, write out the electronic configuration of manganese 2+, iron 2+. These are the boxes we have. Then account for the fact that the iron 2+ ions are readily oxidized to iron 3+ ions, but manganese 2+ ions are not readily oxidized to manganese 3+ ions. Okay guys, let's start with the first question. The first question wants us to define a transition metal. Guys, keep in mind that a transition metal, first of all, is a D block element, right, that forms at least one stable ion with a partially filled D subshell. Good. So guys, a transition metal, like I said, is a D block element that forms at least one stable ion with a partially filled D subshell. That's great. Okay, the next partner wants us to write the electron in box configuration of iron 2+ and manganese 2+. So guys, I want us to start by looking at, though it is not the demand of the question, but I will want us to start by looking at the electron in box notation of the iron element, and that for the manganese element. From there now we can get that of iron 2+ and manganese 2+. So, but guys, in the exam, all you need to do is to go straight to the manganese 2+ and iron 2+. Okay, but I want people to understand it so well. That's why I'm doing this. Okay guys, let's look at that for the iron 2+. So it's the argon core of the, you have the first guy is what, the 2s squared, which means the 4s squared, sorry. We have the 4s squared because this is the 4s orbital. Then there are 2 electrons present there. Then you have the d orbital, that's a 3d6. Why 3d6? Because there are 6 electrons that are found in this orbital. That's why we have a 6 up here. Here we have a 2 because there are 2 electrons found there. So guys, this is the electronic configuration of the iron element, of the element iron. Okay, now let's look at that for manganese. So it is still the argon core of, we have the 4s squared, which means there are 2 electrons found in this 4s orbital. Then the d orbital in this case now has what? Has just 5 electrons. We have 1 2 3 4 5. That's just 5 electrons. So it is now 3d5. Good. So guys, this is the electronic configuration of manganese, and this is that for iron. Now let's see how we can get that for iron 2+ and manganese 2+. Keep in mind, guys, that iron 2+ simply means that you are removing 2 electrons from iron element. Manganese 2+ means you're moving 2 electrons from manganese. So guys, and the closest orbital here is what, the 4s squared, right? So in this case, we are going to simply remove 2 electrons from this 4s orbital and 2 electrons here. So consequently, guys, if we do that, we see that this orbital cancels out, this guy cancels out, and we are just left with this. Good. So now guys, the Fe2+ ions, we are simply just going to have this orbital because this guy cancels out. So this is what we have. But the next guy, then we can label that now as a 3d6. Then for the manganese 2+ ions, we are going to have the argon core of just this orbital. Okay, just this orbital. That's what we have here. Then we can label that as 3d5. Good. So that's the answer to the second part. Now the next part wants us to account for the fact that iron 2+ ions are readily oxidized to iron 3+ ions. But before I continue, guys, I want you people to know that if you look at this manganese 2 plus, right, it is what, half filled. Why half filled? Because the maximum number of electrons that its d orbital is supposed to take is 10, but in this case we have how many? We have just 5. Okay, 1 2 3 4 5. Good. So it is half filled. Why Fe2 plus ions are is what, partially filled, because it contains less than 10, not equal to 5. Okay, good. So it is 6, and 6 is not 5, so it is partially filled and it is unstable. So guys, this half filled orbital is more stable than this partially filled d orbital, and we should know that it won't be easy for this manganese 2 plus ion to go to manganese 3 plus because of the stability of this half filled orbital. So guys, we can say that Fe2 plus ions are readily oxidized to Fe3 plus ions because we have our Fe2 plus contains what, like I said guys, a partially filled d subshell, right, which is unstable, because the question wants us to account for the fact that Fe2 plus ions are readily oxidized to Fe3 plus ions, but Mn2 plus ions, guys, are not readily oxidized to Mn3 plus ions. So we should know that the Fe2 plus ions, as you can see here, it contains what, a partially filled d orbital, which is unstable. Good. So it can easily lose an electron, or it can permit the removal of another electron to form Fe3 plus ions very easily, because Fe2 plus ions, now it is struggling, it is trying hard, it is trying so hard to be stable, and the only way in which it can be stable is to lose one electron, is to lose one. So it is waiting for the slightest opportunity to just lose one electron. Then for the Mn2 plus ions, guys, it is half filled and very stable, so it cannot be readily oxidized to Mn3 plus ions, which is going to be unstable. Good. So guys, that's the explanation in which you can advance. So guys, keep watching the video. You are going to discover so many important things that can help. So let's go on to the. Alright, as we have here, the B part is saying that we should give the transition metal or metal ions used as catalysts in the following conversions. We have nitrogen plus hydrogen, which is giving us ammonia. Guys, just put in the comment section a name for this reaction. The reaction between nitrogen and the hydrogen, which is giving us ammonia. And we also have sulfur dioxide plus oxygen, giving us sulfur trioxide. So guys, again, put in the comment section the name that is given to the reaction between sulfur dioxide and oxygen, giving us sulfur trioxide, and the name for the reaction between nitrogen and hydrogen to give us ammonia. Good. So guys, they want us to give the metal or metal ions used as catalysts in the following conversion. We have these two. Then the C part, group 1 and 2 elements are called S block elements. State and explain the general trend down the group 1 and group 2 in their reaction with water. Then the next, we should give the formula of the S block element, of the S block oxide, that is amphoteric. Then the Roman 2, write out the balanced chemical equation of the amphoteric nature of the oxide in C. Roman 1, that is here. This is C, this is Roman 1. Then the Roman 4, we should still and explain the trend in solubility of the S block surface down the group. Okay guys, let's start with this first name. As you all know guys, the catalyst that is being used here is iron. Okay, we can say finely divided iron, but it is just iron, since they're just asking us but for the name. Okay, it is iron. So guys, like I said, put in the comment section the name of this reaction. If you're correct, I'll congratulate you. If you're wrong, I'll tell you the correct thing. Okay, and this as well. Then guys, the catalyst that is being used here, I'll not tell you the name, you put them in the comment section. So the catalyst that is being used here guys, it's a compound and it is called vanadium pentaoxide. So we have it as vanadium pentaoxide. The formula is V2O5. Good. So that's what we have. Then the C part, we should state and explain the general trend down the group 1 and 2 in their reactivity with water. So guys, we should know that magnesium and we should keep in mind guys that except for beryllium and magnesium, all the group 1 and 2 elements react with water to form soluble hydroxides. Good. But guys, from this first part up to where I have this full stop here is not actually important. I just brought it forth to make you understand it so well. Okay, the answer starts from where you have this full stop. So now the reaction of group 1 elements of 1 and 2 elements water, guys, increases down the group. Okay, the reaction actually increases down the group. That is the trend. That is the trend. It increases down the group and decreases up the group. Guys, why so? It is simply due to what? It is simply due to the fact that let's advance the reason. It is simply due to the fact that the reactivity of one element actually increase down the group, or due to an increase in electropositivity. Okay, due to which increases down the group. Good. So you can either say that it is due to the fact that the reactivity of one element increases down the group, or it is due to an increase in electropositivity down the group. Great. So that's the answer to this part. Then guys, they want us to give the formula of the S block oxide that is amphoteric. Guys, this is a direct question. We know that beryllium oxide is the only oxide of the S block element that is amphoteric. Okay, yes, just beryllium oxide is the only oxide that is amphoteric. Good. So we have it as beryllium oxide. Good. And it's a group 2 element, so that's why we have BeO. Good. Then the Roman 2 wants us to, okay, we have done with the Roman 2. Then the Roman 3 wants us to write out balanced chemical equations of the amphoteric nature of the oxide of this oxide here. Okay guys, with HCl and sodium chloride. So guys, all you should know that an amphoteric oxide simply has both acidic and basic behaviors. In an acid, its acidic behavior is such that because it can react with an acid, because no, it is an acid itself. If it is an acid, guys, that therefore means that it can neutralize a base, right, in a reaction called the neutralization reaction. So guys, as an acid, we expect it to do what? To react with this base, sodium hydroxide. As a base, we expect it to react with what? HCl. Good. So with an acid, when this substance reacts with an acid, that is, it is acting in this case as a base, we are simply going to have beryllium oxide plus hydrochloric acid giving us what? Salt and water, because we know that reaction that a neutralization reaction simply react what? It's simply a reaction in which an acid, in this case we have HCl, and a base react to give us what? This salt, which is beryllium chloride plus water only, guys, only. So we expect to have just these two compounds being formed. Good. Then now, to react with sodium hydroxide, guys, we expect this guy to behave now as an acid, because in this first reaction it was behaving as a base, right, which reacted with an acid to give us salt and water. In this case now, it is behaving in this case now as an acid. Good. So now we expect to have the beryllium oxide plus sodium hydroxide. It is in aqueous medium. In this case, it is in aqueous medium. That is going to give us this, our compound. Okay, we have Na2BeOH, all that 4. So guys, this is the reaction in which we have. These are the reactions in which we have. So just put in the comment section if you have any difficulty, and I'm going to attend to it as soon as possible. And don't forget to subscribe to the channel. If you've not subscribed, guys, subscribe to the channel so that you can have access to watch all our other content. Thank you very much for doing so, guys. Alright, then the Roman 4 is saying that we should study and explain the trend in solubility of the S block sulfates down the group. So guys, we should know that the sulfates of group 1 are soluble, while those of group 2 show variable solubility. Now guys, we should know that the sulfates of magnesium and beryllium, guys, are soluble. Keep in mind that we saw magnesium and beryllium here, right? We saw these two elements here, and we saw that the two elements, they do not react with water, right? But their sulfates in this case, we simply saw that their sulfates in this case are soluble, while the rest are insoluble. Keep in mind, guys, that all group 1 sulfates are soluble. Then the group 2 surface now are now showing variable solubility, and know that beryllium and magnesium are both group 2 elements, so their solubility instead increase down the group, right? Oops, no guys, it instead decreases down the group. So we can see that the solubility of the X block elements decreases down the group due to what, guys? A decrease in hydration energy over lattice energy, or a decrease in hydration energy and an increase in lattice energy down the group. So guys, this is an important hint I want to give. Guys, take note. Each time you're talking about solubility of elements or compounds, in fact solubility of compounds, guys, all you simply talk about is simply their lattice and hydration energies. If lattice energy is more than hydration energy, guys, the solubility is going to decrease, okay? Because if there is more hydration energy than lattice energy, solubility increases. So in this case now, since the solubility of the S block surface now decreases down the group, it therefore means that the hydration energy down the group does what? Decreases, right? While lattice energy increases. Good. So that's what we have, guys. So let's have a look at our next question. The next question is saying that the group 4 elements, as you can see, periodic table are carbon, silicon, germanium, tin, and lead. The Roman one saying that we should give the trend in the structure of the elements from carbon to lead, and the Roman 2 identify the elements which exhibit allotrophy. Give the allotropes of one of these elements. Then Roman 3, these elements exhibit 2 oxidation states. Use the oxides of lead to illustrate this property. Okay, guys, let's dive straight into it. So we should know that there is a clear transition there's a clear transition down the group, guys. From we have non-metals, in bracket we have what? Carbon and silicon, because carbon and silicon, guys, are non-metals and they have giant structures. To metalloids, we have germanium, whose structure is intermediate between atomic and metallic. And guys, we have finally to what? Metallic, in bracket we have tin and lead with giant structures, guys. I think this is a great powerful point, guys. This point is powerful. Okay, it is powerful. If in the exam this question comes, this is what you must give. Okay, you're going to impress your examiners so well. All right, the next part is saying that we should identify the elements that exhibit allotrophy. So guys, we have 2 of them. We have carbon and tin. Good. These are the 2 elements of the group 4 that exhibit allotrophy. Just guys, so keep in the comment section down below if you think there are other elements. Okay, just keep in the comment section down below. Okay, the Roman 2 is saying that we should identify the elements, or we've answered that already. They want us to give the allotropes of one of these elements. So guys, I know that by now we all know that the allotropes of carbon are what? Diamond and graphite, right? But I won't give those examples. I won't give them because I know that all of us know them so well. I would rather want us to give the allotropes of elements that we do not, that are not too familiar to us. Let's bring forth those of tin. Tin, guys, we should know that tin has 3 allotropes. Okay, it has 3 allotropes. We have in the first case we have gray tin, or we can call that alpha tin. We have the next one, we have white tin, or we can call that beta tin. The next we have rhombic tin, in bracket we can call it our gamma tin. Good. So guys, these are the allotropes of tin. Like I said, you can choose that for carbon and give it as diamond and graphite, no problem. But I know that is so common, so I would rather prefer us to give those of tin. That is, we have the gray tin or the alpha tin, we have the white tin or the beta tin, we have the rhombic tin or the gamma tin. Good. So guys, these are the allotropes of tin that you can give. So the next part wants us to that these elements exhibit 2 oxidation states. Use the oxides of lead to illustrate this property. So guys, the oxidation states we're talking about there are the +2 and +4 oxidation states. So now they want us to use that of lead. So guys, we are simply going to take lead oxide and we decompose it. So we have lead oxide, guys. If we decompose this guy, or if we heat lead oxide, we are simply going to have that this is lead 2 oxide, guys. We are simply going to have lead, this is lead 4 oxide, sorry. We are simply going to have lead 2 oxide plus oxygen. So this is what we expect to have, guys. Oops, there was supposed to be a 2 here, guys. When balancing, make sure you put a 2 here. Oops, the equation is not balanced, guys. It's not balanced. So what are we supposed to do? What do we do? Let's see, guys. Okay, maybe there was supposed to be a 2 here. Yeah, there was supposed to be a 2 here, guys. So I'm sorry I didn't put a 2, okay, but put the 2 here. There's supposed to be a 2 here. Good. So guys, lead oxide, lead 4 oxide, you're going to have lead 2 oxide plus oxygen. So this is how we have shown, because this is the plus 4 oxidation state, this is the plus 2 oxidation state. So just this equation is enough to solve the problem. Good. So that is what we have, guys. Then the next question is, halogens are the group 7 elements of the periodic table. We have fluorine, chlorine, bromine, iodine. Then now they are now write out the outer electronic configuration of the halogens. Then we should complete the table below by giving the physical state and color of the elements. Then the B part is saying that chlorine on a disproportionation reaction when reacted with hot concentrated potassium hydroxide. Then the Roman 1, what is a disproportionation reaction? Roman 2, write down an equation for the disproportionation reaction of chlorine with hot potassium hydroxide. Alright, guys, look at that in a different page. Let's look at that. Okay, so guys, I'm sure we saw the equation so well, right? Good. The disproportionation reaction. So guys, let's bring for the equations that we have. Alright, so these are the equations that we have. So now, guys, we should write out the outer electronic configuration of the halogens. It is simply going to be Ns squared Np squared. That's a direct equation. Okay, now the next one, we should complete the table below. Alright, we have the table here. Guys. We should know that. Okay, guys, let's start for fluorine, guys. What's the color of fluorine? We have it to be what's the physical state of fluorine? It is what? A gas, right? Fluorine is a gas. That of chlorine is also a gas. That of bromine is what, guys? What's the state of bromine? Wait, it's a liquid. Bromine is a liquid. Then, guys, that for iodine, as you all know, guys, iodine is a solid. Good. So we have it to be a solid. Then now let's move on to the colors, guys. What's the color of fluorine? What's the color of fluorine, guys? Good. It's a pale yellow color. It has a pale yellow color. Then chlorine, guys, what's the color? From first cycle, from ordinary level, we know chlorine to be a greenish yellow liquid, a greenish yellow gas. Good. Then bromine, what's the color of bromine, guys? A red brown gas. Good. A red brown liquid, sorry. Then iodine, great, it's a black solid. Good. So we have it to be a shiny black. Good. That's a direct question as well. Then the next part is saying now we should define a disproportionation reaction. So guys, it's simply a reaction in which one particular atomic species undergoes both oxidation and reduction reaction. Good. Or it's being oxidized and reduced at the same time. So guys, it's simply a reaction in which one particular species is oxidized and reduced simultaneously. Good. Then the next question wants us to write down equation for the disproportionation reaction of chlorine with hot potassium hydroxide. So guys, keep in mind that they've specified that hot potassium hydroxide because the reaction of chlorine with potassium hydroxide varies. If it is hot potassium hydroxide, we expect to have a separate product which is different from that, which is a cold potassium hydroxide. So with hot potassium hydroxide, guys, we expect to have halide and halide 5 ions are being halide and halide 5 are being produced. Halide means we have the metal halide and we have what? And we have the oxo halide whose oxidation state is 5. Good. So guys, we are simply going to have halide and halide 5 are being produced. So we have chlorine plus 6 potassium hydroxide, guys. That is going to give us, we have the first one, this is the oxo halide, which is whose oxidation state here is 5. Then guys we have what? This is the halide. The halide, that's why I said halide and halide 5 are produced. This is the halide. Then this is the halide 5 that is being produced, the oxo halide, of course, plus water. Good. So guys, this is what we expect to have. That's it. Then guys, if it's for coal potassium hydroxide, we have halite and halite 1 which are being produced. So we will not longer have this 2 here again. Okay, we won't have this 2 here. You won't have the 3. Alright, let's look at the next slide, guys. Let's look at our next question. Okay, the next question is saying that we should consider the following hydrogen halides. This and this. They want us to sketch graphs of boiling points for the hydrogen halides. Then we should explain the shape of the graph. Then the elements across the period 3 of periodic table are sodium to argon. We should complete the table below by giving the formulas of the chlorides formed by the elements. Then which of the chlorides in D1 is a solid ionic chloride, a solid covalent chloride, a liquid chloride. Alright guys, let's start with the graph. So we are simply going to draw our vertical axis and we give that the name the boiling point. Then we draw the horizontal axis, we give that the name the compounds. Good. Then now we start by plotting, guys. Keep in mind that that hydrogen fluoride is going to have the greatest boiling point. Why? Because what it has hydrogen bonds that are present in it, so it is going to make it to have more boiling point. It's simply due to what? Due to the intermolecular hydrogen bond that is present in hydrogen fluoride, which is absent in all the other halides. Okay, it is present just in this man, so it's going to make it to have a higher boiling point as compared to all the others. Good. So let's start by seeing if we can plot our curve. So we simply start by locating a suitable point where hydrogen fluoride can be. Then now hydrogen chloride is going to have a smaller boiling point than hydrogen fluoride, so we are going to name this guy hydrogen fluoride. Then we locate that for hydrogen chloride, which we have it here. We give it the name hydrogen chloride. Good. Then we locate that for hydrogen bromide as well up here. That's what we have. Then we give that the name hydrogen bromide. Good. Then we locate the last one now for hydrogen iodide and we give it the name hydrogen iodide. Good. So now we connect all these are points now using suitable straight lines. So guys, this is a graph in which we are to sketch. So this is the graph. Then the next question wants us to explain the shape of the graph. Good. Like I said, guys, normally the boiling point increases with increase in van der Waals forces, and the van der Waals forces increases normally with increase in molecular weight. But hydrogen fluoride, as we saw here, has a much bigger hydrogen bonding, so it has a much larger boiling point. Okay, that is due to the increase in the intermolecular hydrogen bond that is present within the molecule. So guys, if you want to explain, we can tell them that the boiling point increases from HCl to hydrogen iodide due to an increase in the van der Waals forces, but we should also know that the exceptional high boiling point of hydrogen fluoride is due to the strong hydrogen bonds between the molecule. So we've simply explained the shape of this curve, guys, that it increases from hydrogen chloride to hydrogen iodide. Then this guy has an exceptionally high boiling point due to the van der Waals, due to the hydrogen bonding that exists between the molecules. Good. So now guys, due to space constraint, I will answer the next question directly on this table. Okay, we'll just put them on this table. So the next one wants us to complete the table below to give the formulas of the chlorides formed by the elements. So guys, like I said, I'm sorry for the limited space. We'll just complete everything here. Okay, we'll just complete here. So the chlorides of sodium, of course, we all know that to be what? Sodium chloride, right? Good. So we all know that to be sodium chloride as we have here. Guys, know that knowing the chloride is not the issue here, but how to bring forth the correct chemical formula of those chlorides, that is what matters actually. Okay, good. So we know that for sodium to be sodium chloride. Then that for magnesium as well, we know it to be magnesium chloride. Good. Then aluminium as well, you can bring for the dimer of aluminium, no problem. That's Al or Al2 Al2, that's Al2, then Cl6. Good, that's going to be accepted. But I'm going to bring the most simple form, okay, the most simple form. So we are going to have AlCl3. Good. Then now for silicon, guys, of course we all know is a silicon tetrachloride. Good. Then that's for phosphorus, we know it to be PCl5, or you can write PCl3, it's still good. Then that's for sulfur, guys, we have S2Cl2. That's for chlorine, it is just going to be the chlorine molecule, guys. And argon is what? Argon is already a stable element, right? So it has no chloride, it does not form compound, so we can just put that with a dash. Good. So guys, like I said, you could still choose to write PCl3, that's all up to you. But if you write PCl3 and PCl5, no problem, but you won't have any extra mark. So in this case, and there's also another chloride for sulfur, so maybe I should indicate this one. So we have SCl2. Good, you can still give this one and you'll be on track. Great, guys. So guys, don't forget to subscribe to the channel to have more contents. Don't forget to subscribe, guys. Then the next one is asking us which of the chlorides in D1 is a solid or ionic chloride. Guys, this is a direct question. As you all know, the two solid ionic chlorides we have is what? Sodium chloride and magnesium chloride. So we can either bring forth this or this, okay? We can either bring forth either sodium chloride or magnesium chloride, but in this case I'll just indicate two of them. Good, two of them. Then now next is solid covalent chloride, guys. A covalent chloride, we can be talking particularly about PCl5, okay? PCl5 is a solid covalent chloride. Then a liquid chloride, guys. A liquid chloride, guys, we should be talking on about silicon tetrachloride. Good, that's the tetrachlorides of silicon. Silicon tetrachloride is a tetrachloride from the group 4 elements, namely we have carbon, silicon, germanium, and so on. So silicon belongs to them. Alright, so guys, let's move on to the next slide. Okay, now the next one wants us to give the formula of one oxide of the element, which is a giant ionic. B, we have giant molecular. Then C, giant oh my god, okay, the next one is simple molecular. Good. So guys, as you all know, the first one, guys, we should be talking about magnesium oxide. Magnesium oxide is a giant ionic oxide, as well as sodium oxide. You could still give iron oxide, okay, aluminum oxide, sorry, you can still give aluminum oxide. It is still a giant ionic oxide, okay? Any of them, any one of them is good. Okay, now the B part is asking for giant molecular. Okay guys, for giant molecular we simply give what? Silicon dioxide. It's a giant molecular compound. It's a giant molecular oxide. Good. Then guys, the C part is asking for simple molecular. So guys, for simple molecular we are going to give sulfur dioxide, okay? It's simple molecular. All right, so guys, don't forget to hit the subscribe. Don't forget to subscribe so you're going to have access to all our content, guys. We have contents in our channel. We have so many of them, guys. They are almost up to 100, okay? We have almost up to 100 contents in our channel. So guys, hurry check them out to prepare for your exams so well, because we offer contents in biology, chemistry, physics, mathematics, further mathematics, computer science, ICT, and so on and so forth, guys. You will love it, okay? You will love it. So guys, the next one is saying that sulfur and its compounds are used in the industry and in agriculture. Give one use of sulfur and its compounds in the industry and in agriculture. Alright guys, in the industry, then the next one is saying that we should give an example of a compound of nitrogen in the -3 and the +5 oxidation states. Alright, so guys, let's start with in the industry. So guys, in the industry, guys, we simply know that sulfur is used in the manufacture of sulfuric acid. Good, we use sulfur to manufacture sulfuric acid. Good. Then now in agriculture, guys, it is definitely used as what? As a fertilizer. It's used as a fertilizer on farms, such as we have ammonium sulfate. This is a fertilizer that is being used. All right, so now the next part wants us to give an example of compounds of nitrogen in the -3 and +5 oxidation state. So the first guy that does a -3 oxidation state, guys, simply we have ammonia. Okay, we have ammonia, which has an oxidation state of -3, then nitric acid, guys, which has that of +5. Good. So guys, we've come to the end of our video today, and don't forget to hit the subscribe button right now to have more content. And guys, you need to go back to our channel and answer the homework I gave people. Okay, the homework, I was asking for the name that is given to the reaction between nitrogen and hydrogen to give us ammonia, and that for sulfur dioxide and oxygen to give us sulfur trioxide. So guys, do the homework, just put it in the comment section and I'm going to reply before you notice it, the fastest method as possible. So guys, congrats to those who have watched the video from start to finish. I definitely appreciate, and subscribe to the channel, guys, if you've not done so. Hit the like button. Don't forget to like the video, because that does motivate us to produce more and more content for you guys, and we are going to do that for you guys once we see so many subscribers. Share the video out with your friends so that they can have access to good content that can help them prepare for their exams. Guys, don't show them after the exam, but show them before the exam, so they're going to prepare so well for their own exams and they can pass, just like how you watching this video now and have subscribed to the channel is going to pass with the best of A grades. So guys, feel free to contact me if you have any difficulties, and I'm going to reply to you as soon as possible. Thank you very much, and have a blessed and a great day.